This video is going to be about projectile motion. We're going to deal with projectiles at an angle and projectiles perfectly horizontal going off a cliff. A projectile is an object that is launched. Given, you throw it, shot out of a cannon, you've launched it in some way, shape, or form, but the only thing acting on the object once it is launched, once it's got into motion, is gravity. So at that point, it's acceleration. The only thing that's causing it to accelerate is gravity. The rest of the stuff, what caused it to get into motion, the launch, is ignored. We find out what velocity it came out of the cannon with, what velocity it came out of the gun with, whatever the case may be. We just find that we get that initial velocity, and then gravity is the only thing acting on it. Two things that we like to make sure we mention is that there's acceleration in the y and acceleration in the x. The acceleration in the y is your gravity, and we typically like to use 10 meters per second squared downward. It can be negative and it could be positive. As long as everything in the equation is all going in the same direction, they all have a direction agreement, we can keep everything positive. The moment you have acceleration acting against a velocity vector that's going up, then you have to have the acceleration be negative. Now, acceleration in the x direction does not exist. So that means that the object that is traveling in the x direction, if it has any velocity in the x direction, the velocity would then be constant. And we like to keep things that way, so it makes things really easy to calculate for velocity, distance, and in time if we need to solve it in the x direction and have enough variables. So we're going to start with looking at a horizontal projectile. And a horizontal projectile is usually seen coming off a cliff. It has initial velocity coming off a cliff and then travels in a projectile pattern after that. And the other one is a projectile at an angle where we have some angle that is launched up into the air and it travels and lands on the same height it was launched at and lands on the ground. Now, I've drawn a picture here that looks identical to our projectile horizontally here in the middle of our angle projectile picture to represent that if you take the second half of the projectile at an angle, it is identical to a horizontal projectile. It's identical. So it's pretty nice if you can separate half of it. If we're going to need the second half of the projectile at an angle, you can treat it just like a horizontal projectile. The velocity in the y direction is 0 at that top point, and it has a horizontal velocity just like a horizontal projectile. Now on the way up on a projectile at an angle, the object is slowing down. So velocity in the y direction is decreasing, and the velocity hits 0 at the top, and then the velocity in the y direction is increasing, so the object is speeding up. My arrows here are talking about the velocity speed, not necessarily the direction that the velocity vector is going. So on the left side, the velocity is slowing down. You start with a great velocity in the y direction, and it's slowing down to 0 at the top, and then it is speeding up on its way down. And so I've represented the arrows next to velocity in the y direction as speeding up or slowing down, not necessarily the direction that the velocity is going at that moment. So let's solve a horizontal projectile problem. We have a cliff that's 20 meters tall, and we're going to launch something off that cliff with the velocity in the x direction at 10 meters per second. So what we first have to do is separate things into x and y, and we can write down all of our givens, x and y, velocity in the x being 10 meters per second, acceleration in the x being 0, and velocity, and then velocity in the y is 0 meters per second. So it's like a ball that's dropped, and then gravity begins to act on it, so it has 10 meters per second squared, and the change in y is 20 meters. What we're looking for in this equation is how far off the cliff it's going to travel. So we're going to start with a very simple kinematic equation. Change in y equals initial velocity times time plus 1/2 at squared. And since our initial velocity in the y direction is 0, we're able to cancel that out, and we end up with 2 change in y over a square rooted equals t. And you plug in all of your numbers that you have there given, and you'll get 2 seconds. And that makes things very nice, because then we can just take that time over to the velocity or to the x direction material and plug it into the constant velocity equation, knowing that acceleration is not affecting horizontal velocity at all, so that velocity in the x direction is constant, so we can use the constant velocity equation, v equals change in x over t, and reorganize it for change in x, plug in our numbers, and we get a very simple 20 meters. It's very nice. It's very nice when things happen that simple. And that should be all review. The other one we're going to do is projectile at an angle, where we're going to have one launched at 100 meters per second at an angle of 30 degrees. There's no acceleration in the x direction. We have an acceleration due to gravity in the y direction. And since it's going to start from one height, travel up into the air and come back down and land at the exact same height on the other side, its y displacement is 0. It may have changed displacement, started somewhere and finished somewhere else in the x direction, but as far as its height goes, it goes up in the air and comes back down to the exact same height. So its displacement in the y direction is 0. Makes it real nice for this equation. So we're able to take we have to split the velocity vector into 100 meters per second and split it into its horizontal and vertical vectors, its components basically. So we have 100 cosine 30 and 100 sine 30 based on the angle of 30 degrees. And I get our velocity in the x direction to be 86.6 meters per second and our velocity in the y direction to be 50 meters per second. And we'll take those velocities and we'll plug them in here into our given. So velocity in the y direction is 50 meters per second up. I'm going to go back for a second. It's 50 meters per second up. So since our velocity vector is up, it is going up into the air. That means that our acceleration is not in direction agreement. Our gravity is not in direction agreement, so we have to add that negative there. Alright, so you see that I've added that negative there. It's in the same color, so it looks like a triple equal sign, but it's really an equal sign with a negative over the top of it. So make sure you add the negative when needed and when the direction agreement does not happen. So we'll add the velocity in the x direction is 86.6 meters per second. The change in x, we don't know. We want to know how far it's going. Well, we can use y stuff knowing that it doesn't change displacement in the y direction. So right off the bat, we're able to use change in y equals v naught t plus 1/2 at squared and get rid of the displacement in the y direction. And then move v naught t to the other side. Okay, and we know that because the change in y was 0. So negative v naught t equals 1/2 at squared. Whoops, got a plus sign there. There we go. Alright, that allows us to cancel t on the left side and one of the t on the right side. We'll get rid of that square, so we're left with 1 t on the right side. And we have move the half over, divide by a, and we get negative 2v naught equals t, which comes out to 10 seconds. And then we plug that 10 seconds into the simple constant velocity equation, and we find that the change in displacement, or how far it went, was 866 meters. So what we're worried about now is how high did it go. That was very simple to find out how far. Now we got to talk about how high. So we're only worried about half of the parabola. I'm going to do the left half of the parabola. So it's going to initially start with 50 meters per second traveling up, and then it's going to finish with 0 meters per second at the top of the projectile. So we have to make some adjustments to our givens. So the first thing is we have no x data. None. How high it goes depends only on vertical stuff, so we get rid of the x stuff, and our change in displacement in the y direction is now a number. It is not 0 anymore. It's going to go up in the air, and we want to find out how high it went at its peak. So we're assuming it's not coming back down for our calculation, or we're just finding out how high it was at its peak. Either way, that forces us to get rid of the change in y at 0 meters, and it makes our 50 meters per second an initial velocity. So you see that I've added what appears to be a dot, but that's supposed to be a 0. So v naught equals 50 meters per second. And then v, or final velocity, is 0 meters per second. And our change in y is what we're looking for. So we use v squared equals v naught squared plus 2a change in y. V squared, since it's 0, you square 0, it's nothing, and we can get rid of it and move the v naught squared to the other side. So we have negative v naught squared is going to equal, or divided by 2a, is going to equal the change in y. The thing about this, that negative applies to the v naught squared after the fact. So what we'll do is we'll plug in our 50 into a parentheses squared and then put the negative outside of that parentheses. And then down on the bottom we put 2 times a negative 10. What that will do is allow our negatives to cancel each other out. 2 negatives will make a positive, and that equals the change in y at 125 meters. So this should be a complete projectile review of what we did in AP Physics 1. Tomorrow we should be able to attack some things: free fall, projectiles, constant velocity, things accelerating in the horizontal direction, and then try to, if we have time, dive into projectile problems where we launch it off a cliff at an angle and it travels off the cliff lower than where it was launched. It's kind of like hitting a tee shot in a golf match where you have an elevated tee down to a green that's well below your feet, and so you got to account for that extra distance it would travel horizontally and possibly vertically. So we'll try to dive into that if we have time. But we'll see you in class tomorrow.